We can calculate percent compositions from formulas, but what if we don't know the formula? We can actually calculate the formula if we know the percent composition. And the percent composition is something that we can determine by an experiment. We can take a compound and break it down into its elements and weigh them and use that information to figure out what the formula is. But the formula that we get is called an empirical formula. Empirical means derived from or guided by experience or experiment. This is a practical thing. The empirical formula is going to give the smallest whole number ratio of each kind of atom in a compound. It doesn't give us the specific number of each type of atom in a molecule. And the molecular formula, which does tell us how many atoms of each element are in one molecule, is always going to be a whole number multiple of the empirical formula. So that probably didn't make a whole lot of sense. But now there should be a slide here. Okay, I'm going to make a slide. We'll go with the chalkboard. So if we have something like, here's a formula. Not a compound that you've learned how to name, but there's a formula. This is the formula for benzene, just in case you're interested. C6H6. There's actually 6 carbon atoms and 6 hydrogen atoms in a discrete molecule, and they're all bonded together, kind of like a family unit, and they go around and they do stuff, I guess. They go to Disneyland. This is the molecular formula. This tells us what's in the molecule. The empirical formula is like the reduced fraction version. Okay, this is a ratio of 6 to 6. That's the same as 1 to 1, isn't it? The lowest ratio is CH. This is not the formula for the molecule, but this does give us the ratio. This is the empirical formula. So for benzene, the molecular formula is 6 times the empirical formula. Let's look at water. This is the molecular formula for water. Is this the lowest ratio, 2 to 1? It is. It is also the empirical formula. The molecular formula is a whole number multiple of the empirical formula. It's multiplied by 1. Sometimes the empirical formula and the molecular formula are the same, and sometimes they are not. Here's another compound. Molecular formula. What's the empirical formula for that compound? CH. C6H6 and C2H2 have the same empirical formula, but their molecular formulas are different. Okay? If you look at a formula and the ratios are not the lowest, like this one, C6H6, it's definitely the molecular formula. If it's the lowest ratio, you can say it's the empirical formula. You can't necessarily tell if it is also the molecular formula or not. But if it's something that can be reduced, let me think of another one. Like P2Cl6, is that an empirical formula? No. That's a molecular formula because that can be reduced to PCl3. This is definitely an empirical formula. Okay? So how do we calculate an empirical formula? Here's an example of how that could be done. You can actually decompose water using a 9-volt battery. And you could try that at home. You can take a 9-volt battery and drop it in a cup of water, and you'll see bubbles forming from both terminals. And one terminal is generating oxygen gas, and one terminal is generating hydrogen gas. So you can decompose a sample of water in the lab, and you can measure the amount of hydrogen and oxygen that are produced. We've got 3 grams of hydrogen and 24 grams of oxygen. So how can we figure out what the formula for the compound is? The formula for a compound tells us ratios of moles or ratios of numbers of atoms, and these are masses. So for those of you who like lists of instructions, here's a fabulous list of instructions to find the empirical formula. Doing these calculations is not hard, it's just tedious, and the hardest thing is remembering what to do next. So you start with the masses of each element. In that previous slide, we were given the mass of oxygen, the mass of hydrogen. Sometimes you'll be given percent composition. And if that's the case, then just say, okay, I'm going to pretend that I have a 100-gram sample, because then the masses in grams are the same as the percentages, right? If it's 25% hydrogen and I have a 100-gram sample, I have 25 grams of hydrogen. So that makes it easy. You got to start with masses. Then you convert them, the masses, to moles using the molar masses of the elements. The train is having its commentary. Yeah, I don't like step 3 either, but this is what the book teaches. So it says to write down a pseudo formula for the compound using the moles of each element as subscripts. You can do that. I don't. We're going to divide all the subscripts, which would be the moles of elements, by the smallest number of moles. We're trying to get a whole number ratio of moles. And when we just calculate the moles, we're going to get weird fractions, and it's hard to make anything out of them. So we need to get to ratios. So we're going to take them and divide by the smallest one, and then we will always have one that's exactly 1, right? Because it got divided by itself. And the others will all be greater than 1. And sometimes they're just beautiful whole numbers and we're good, and other times they're not, and then we have to multiply until we get whole numbers. And we'll do examples. So here's an example. A gaseous compound containing carbon and hydrogen was analyzed and found to consist of 83.65% carbon by mass. Determine the empirical formula. They only gave us one number. This is a percent. We are going to assume a 100-gram sample. So in a 100-gram sample that's 83.65% carbon, what is the mass of carbon? It's 83.65. 83.65%, right? This is what you do. You erase the percent and you write gram. That make more sense? Grams of carbon. We need to convert grams of carbon to moles of carbon. We learned how to do that today. We multiply by moles and we divide by grams. What's the mass of 1 mole of carbon? 12.01, right? So we've got 83.65 divided by 12.01. Now, this is a good place to keep extra significant figures. Do not round too much here. You're going to have problems. 6.9650 moles of carbon. They didn't give us any information about the hydrogen. If 83.65% is carbon and there's only 2 elements, what's the percent of the other one? 16.35. 100 minus that. 100% minus 83.65% is 16.35% hydrogen. Because it has to add up to 100%. So I'm going to write that down, 16.35% hydrogen. And then I'm going to erase the percent and change it into grams. It looks like magic, but it's not. And we're going to convert to moles of hydrogen. We look on the periodic table, 1.008. 16.35 divided by 1.008 equals 16.2202 moles of hydrogen. Now, we can't just round those and say it's a ratio of 7 to 16, because it isn't. So what we're going to do is we're going to take this number that is the smallest, and we're going to divide each of them by the smallest. So I'm going to divide this by 6.9650. And so that gives me 1. And I'm going to take this one and divide by 16.9650. And I get 2.3288.
Why did you do that?
I'm looking for the ratio. So I'm taking the bigger one and dividing by the smaller one. Because I don't want to end up with more fractions. I want to end up with whole numbers. And so this is a step in the right direction. This is better. Here we've got this one divided by itself is 1, and this one divided by the other one is 2.3288. So you take all of them and divide by the smallest. Yeah?
Why did it put 16.35 hydrogen?
Because we were told that the compound contained carbon and hydrogen.
But isn't it 60.39?
What did I do? Oh, I wrote a wrong number up here. I'm sorry. Because 100 minus 83.65 is 16.35. And then I got it right down here. Who knows? Yeah, but those are the sorts of... This is not a whole number. And we can't just round this off. So what we're going to do is we need to keep this ratio the same. We're going to multiply by numbers to find out what we can do to get it to be a whole number. Now, if you understand decimal equivalents of fractions, 1/3 on your calculator, if you take 1 divided by 3, it's going to give you 0.333 forever. That looks a lot like 0.3288. That's really close to 0.3, right? This is really 2 1/3. So if we multiply by 3, we're going to get a whole number. But I'm going to pretend that we didn't think of that. This is the trial and error method, which most 3A students like. So you take that number and you multiply by 2. See what you get. 4.6576. That's not super close to a whole number either. Okay, that didn't work. So multiply by 3. Start with 2, then go 3, 4, 5. Times 3. Now I get 6.986. That's really close to 7. So if I multiply this by 3, I get 6.986. If I multiply, I have to do the same thing to this one. I multiply that by 3, I get 3. trying to get 3 anyway. The guideline is that it needs to be less than 0.2 from a whole number. So if it was between 6.8 and 7.2, you could round it to 7. But you can't just go rounding things willy-nilly. So this we can round now to 7, and we'll call that 7. So here we've got 3 and 7. Those are the subscripts in the formula for this compound. Carbon is 3 and hydrogen is 7. Now try this on your calculator. Take 7 and divide it by 3. And you get 2.333, which is really close to this ratio, right? Because that's the ratio, it's 3 to 7. So that's the empirical formula for that compound.